Everybody, welcome to Studio 64. My name's David, and I've been searching the interzones for some more science, space, and tech news to share with you. And I came across this at Science Alert. Yes, physicists demonstrate room temperature quantum storage in 2D material. This should be interesting. Now, as I say, I'm not a scientist, I'm not a physicist, a materials science person. If there are anybody watching this video, any of you out there, scientific type people, physicists, please feel free to comment down below the video because I'd love to hear from you. This is absolutely amazing. I love sharing science, space, and tech news, and I'm just a science student of all sciences. Doesn't matter whether it's astronomy, anything material science like this. I just love it all. Computer science, it's just fantastic. Microscopic chinks in material just several atoms thick have the potential to advance a multitude of quantum technologies, new research shows, getting us closer to the widespread use of quantum networks and sensors. Now, right now, storing quantum data in the spin properties of electrons, known as spin coherence, requires a very particular and delicate laboratory setup. It's not something you can do without a carefully controlled environment. And as usual, I'll leave the link to the main article below the video so you can pop in and check out some of these embedded links if you want to go for a bit of a deeper dive behind the main article. Makes for a very interesting read, believe me. Now here, an international team of researchers managed to demonstrate observable spin coherence at room temperature using the tiny defects in a layered 2D material called hexagonal boron nitride, or HBN. This is really interesting. Again, I'm not a scientist, but I've got a technical type mind. So this, to me, this is really a great breakthrough, because if we can get it at room temperature, because there's a lot of stuff that we, like in other areas of science, we can only do it like Kelvin, which is, I don't know what it is, minus 200 degrees Fahrenheit. Anybody out there can correct me on that, please tell me. So that doesn't work at room temperature, but this is going to be absolutely amazing. Yes, the results show that once we write a certain quantum state onto the spin of these electrons, this information is stored for around 1/1,000,000th of a second, making this system a very promising platform for quantum applications, says physicist Carmen Gilardoni from the University of Cambridge in the UK. Yes, very interesting. Now, this may seem short, but the interesting thing is that this system does not require special conditions. It can store this spin quantum state even at room temperature and with no requirement for large magnets. Now, this is really good because it's just a start. People go, well, a millionth of a second, that's useless. But it won't be useless once they get it to a usable, a usable amount of time. It's kind of like, I don't know what that time would be, as again, I'm not a scientist, but I can see the potential in this. It's very much like what we're doing with nuclear fusion at the moment. They might get a stable reaction for 6 minutes. Oh my God, that's incredible. 6 minutes. I think that was the figure. But that is incredible in the state of in the state of nuclear fusion at the moment. Because if they can go from microseconds, like a millionth of a second in, a stable reaction in this, and a millionth of a second in a stable reaction in nuclear fusion, right? In nuclear fusion, and then go to 6 minutes, 60 minutes in fusion won't be that far away, hopefully. And 6 minutes and then 60 minutes in this at room temperature, in this quantum, this quantum applications, this platform for quantum applications is possible. Is it quite what's the expression? Proof of concept yet? I don't think so, but it's very, very interesting. Now, the layers of HBN stay locked together through molecular forces built into the material itself, but defects can emerge when the material is synthesized or processed. This gives tiny places where electrons can be trapped. And this is why I find all this sort of thing so exciting, because I can see parallels or, analogies, if you like, in other areas of science, and I can see how we're progressing. It's absolutely amazing, absolutely amazing. And again, by leaving the link to the main article below the video, you can pop in and check embedded things like these longer videos with quantum computing could revolutionize space exploration. Check those out. They're very interesting videos. Not only were the researchers able to trap and observe electrons in HBN defects, they were also able to manipulate them using light. This is a first for experiments of this type at normal ambient temperatures, and that's the key. Normal ambient temperatures, not at some minus 450 degrees, or in the case of of nuclear fusion, we have to have an operating temperature generate power so high, it's like the sun, and it would be completely impractical. Now we're getting to the point where we can contain something stable for 6 minutes with nuclear fusion, and in this case, it might be only a thousandth of a millionth of a second or whatever it is, but that's the first step. And the next thing you know, we'll be doing it for a minute and 5 minutes and 10 minutes or whatever it's necessary to make it practical and functional. It's amazing. Based on the measurements taken by the team, the use of HBN shows promise as stable quantum storage. Even if quantum states can only be stored for a small fraction of a second right now, the signs are that it could be eventually scaled up. I'm sorry, I'm just really excited about this because I can see where it is. People look at hard drives and go, well, that's only 1 gigabyte. Are you kidding me? That was a massive leap back in the day. And now we go, oh my God, we've got an 8 terabyte hard drive. Isn't that fantastic? Are you kidding me? That's nothing. You give it a few more years and you'll have 8 terabyte storage in your bloody hearing aids. It's a start and it's just fantastic. Working with this system has highlighted us to the power of the fundamental investigation of new materials, says physicist Hannah Stern from the University of Manchester in the UK. Now, as for the HBN system, as a field, we can harness excited state dynamics in other new material platforms for use in future quantum technologies. Now, keeping quantum states and quantum information stable and protected from interference is an ongoing challenge for scientists who are continually looking for new materials and new techniques to improve stability. This is where we're getting the cross disciplines of science come in. Material scientists and physicists and engineers to build the actual mechanical stuff. I love this. I absolutely love it. I love it when somebody like me who has a general knowledge of all things computing, I understand about networks and how they operate. I'm not a networking specialist, but I can speak to a networking specialist who might not understand anything about code, a lot about coding, but I know how to code. I'm not as good as half you guys, 3/4 of you guys out there, but I understand enough about coding to go and talk to the guy who was the hardware engineer or the networking guy or the graphic artist doing the website the website interface or the app person or something, and I can look at all these guys and go, this is really exciting. Whereas a coder will go, well, that's hardware. I don't know anything about hardware, but then I can look at the hardware and go, this is a breakthrough in hardware. And I can talk to the coder and go, this is going to make your code a lot quicker, and vice versa. I just have a little knowledge of all these different areas of computing, and I'm trying to build up a knowledge in my head of all different areas of science, from astrophysics to material science to nuclear fusion and all that sort of stuff, and I can see that, hey, we can get this guy from this area, we can get this lady from this area, this scientist from this area, and look, this person's working on something in biology, or someone's a geologist or something. So let's get all together and we can have a really, really amazing team that, this is incredible. You could build a team with all different area disciplines. And it's just, I think it's fantastic. I'm sorry, I get all excited down in my nerdy nether regions. But then again, my personal life is no concern of yours. The team is now investigating ways to increase the spin storage time beyond a millionth of a second, improve the reliability of the defects and the quality of the light emitted from it. This would have been very similar to when they were going from magnetic cassette tape drives to floppy disks, which are a similar medium, I guess, and then got those right, because I remember floppy disks had a lot of errors, compared to a hard disk. And then eventually a hard disk came along, and now we've got solid state drives, and this is just amazing. It's like the first steps on a digital journey that to me is just amazing. As progress is made, slowly but surely, we'll be able to develop more advanced quantum sensors, able to monitor minute changes in the universe, and quantum networks for super fast, super secure information transmission. Hooray! We'll be able to upload that stupid TikTok video a lot quicker. Windows could reboot a lot faster. And we could also help, cure cancer, but nobody cares about that. Human beings are fascinating, aren't they? Yes, I can be banned off Facebook a lot quicker now. Super fast, secure information transmission. You're on YouTube. You said a word that we think our artificial intelligence mistook for being a racial slur. Banned. Oh, that happened yesterday. Oh, wow, that was quick. It'll be time-traveling censorship. Incredible. Each new promising system will broaden the toolkit of available materials, and every new step in this direction will advance the scalable implementation of quantum technology, says Stern. The research has been published in Nature Materials. Absolutely amazing. Absolutely incredible. I'm very excited about it. Again, I don't claim to be a scientist. I just love all science and sharing stuff like this because I can see the potential. I can, as I say, an analogy, put it back to the early days of, getting a cassette tape storage for your computer, reel-to-reel tape, then cassettes, and then floppy disks, and then physical hard drives, and then solid state. Because we use solid state drives and mechanical hard drives like they're normal, right? I can remember back in the day when people were talking about massive hard drives, but they couldn't get the storage times right. You know what I'm trying to say? They couldn't get it right. Eventually, they got a stable system. This is what's happening right here, right now. We're getting there. It's fantastic. All right, well, my name is David. Thanks for joining me for another Studio 64 Science, Space and Tech News update. I shall see you in the next one. If you enjoyed this video, please like, share, subscribe. I'd greatly appreciate it. If you're up for it, drop a comment down below the video because I'd love to hear what you think. All right, take care. And as I always say, if you can't be good at it. And as I also always say...
Did IQs just drop sharply while I was away?